So, hey everybody. I'll go we're running a little short on time. So I have a movie here. I'll skip through that till the end and then I'll show it at the very end. So my name's Cameron. I work for a company called SICK. Wonderful name, of course. Well, in California slang, it makes sense to a lot of us surfer types because things that are good are sick. But it's actually someone's last name. Edwin Zick, in German pronunciation, was quite the inventor in southern Germany back in the 40s. And from his kind of optical expertise, grew this enormous company that I now work for. We're very much an international company, very well spread across most of the world. We're probably around 1.2 billion at this point in time. We're very broad in terms of technology. Process automation is one huge group. Factory automation, which is my kind of expertise, and everything kind of consumed in that, as well as logistics. All of these things are sort of merging together now, I think, with Internet of Things and connectivity. Here's a quick snapshot of all the stuff just in factory automation we sell. So photoelectrics, proximity, all of these are obviously sensors. We're talking about sensing here with the robotics. So basically, these are the devices that feed that information up to the Internet of Things and allow people to make decisions on what's going on. So all the way up to full 3D vision and really kind of things that can give you navigational abilities. These are probably the funnest sensors, I think, as far as what's coming. These are really giving eyes to automobiles and tractors and forklift trucks. So in the years of development, we invented auto collimation, which is a neat principle which allows you to basically use the same path of light going out as the same path coming back. This was kind of the basis for the very first light curtain. This was in Daimler-Benz in the 50s to keep people's hands from getting crushed in a metal press. Gas measurement using light, time of flight sensors, which is kind of the basis for a lot of the navigation sensors we use today. 2D code reading, 3D cameras. So we started getting into 3D around the early 2000s. This is using basically a scanning laser and an encoder input to give us a 3D rendering of an object you can see in the bottom corner there. And as autonomous vehicles grow, we're growing into that as well with navigation on landmarks with cars looking at a tree or a stop sign or different things to kind of understand where you're at. And now at the cutting edge, super high speed 3D color cameras. These are working at 35 kilohertz, imaging things like grapes and bread and hamburgers and whatnot. So we'll hold on this for a little bit. And really to the basis of what information you can gather. So in the 50s, this was a photoelectric switch. It turned on, it turned off. This is the only data you could really get out of it. And as we evolved as a company, we realized, why not make the decision out where the actual detection is happening? Why not have the sensor telling you, I'm dirty, come clean me? We have this special output from this thing that can literally indicate to a maintenance guy, there's nothing wrong, but I can tell there's dust accumulating on my lens, send a maintenance guy to clean me. It can monitor temperature, sensor health, which is also involved in how long is the LED going to run for before it needs to be replaced, or changing settings remotely. So if I'm at Tesla, I don't need to walk a half mile to some machine to adjust something. I can just access it via I/O link and then make adjustments there. And as well as cloning, I smash a sensor with my forklift. I don't need to go reprogram the thing. I can just plug it in, program it over the network, and interact with it. So all of this is in lieu of power consumption. You talked about, Charlie. We can make sensors smaller because we don't need to have buttons and displays on them anymore, and we just don't need as much stuff kind of out there. And this is kind of what a network like that looks like. So this is I/O-Link. We're talking about a lot of different communication protocols. Another one from Germany, really. And I think I don't know why these things come from Germany, but I think there's more collaboration amongst quasi-competitive companies there that will get together and decide, okay, let's do IO-Link, let's do EtherCAT. So maybe it's sort of the socialist underpinnings of that country, but a lot of these awesome technologies come from there. So basically we have IO-Link, which is a sensor connective network. It is only between sensors, essentially, where you can create little logic schemes between them. You can timestamp events. This data then bubbles up to IO-Link masters, which are gathering that data, and this is basically our field bus, kind of out there on the factory floor. We're bubbling that up to a PLC in this case. This could be an industrial PLC or a PC, and then from there we're going up to the cloud or up to management. So this is the basic snapshot of industrial SCADA, but what we're really bringing in is as many devices as possible to feed that data up. Things that were considered stupid before are now really the key data drivers of a factory. And it works quite well, but I would say that the trickiest part is maybe this bit of the implementation. So you walk into a big customer like a Tesla, and you say, I've got all these great features on my sensors, and they're like, well, how the heck do I get that from the sensor to somewhere who can make a decision? That's tricky, getting the IO-Link master, and then the software involved with interfacing with that. These are always challenges with a fast-moving company. And then the other part is above that, you can tell the customer, hey, you don't even need maintenance people. I can remotely monitor your sensor from my house, and if something's going wrong, we can send maintenance people, but in a lot of cases, they don't want to give you a link to the outside world. So these are challenges we often have to overcome in dealing with this stuff. So in the real world application, kind of what you can do, timing is a huge thing, which IO-Link gives us great capabilities where we can, instead of having this monitor a sensor input all the way back up to a PLC, we can monitor just within the sensor, maybe talking to a drive. So this way I can get really lightning fast reaction times and start using the sensor as an inspection device. This is a wood cutting application. In my world, we're often dealing with two sensor inputs watching a robot go by. And if we can get really good low jitter and high parity on the sensor input, you can get better positioning accuracy. So this is something we always drive for. Wood products drives a lot of this. It seems like the efficiencies gained in implementing systems like this, especially for the wood guys, the USNRs, the Weyerhaeuser, a lot of this coming out of Sweden as well, drives the market because they can implement this stuff more easily. When I try to implement these sort of things at an Intel or whatever, because of the copy exact rules, we're often stymied. Another big benefit of this, and which bleeds into my next subject, is it cuts down a lot on wiring. I don't need to wire from a sensor all the way home run back to the controller. I can wire sensor to sensor or sensor to an IO-Link master. And where I was previously just moving power, I'm actually using these same wires as communication infrastructure. So this is a good example of how we can, use existing wires that are there, but now we can move communications over them. This is a sensor connector. We do the same thing now with encoders. So I can actually, connect an encoder to a drive with less wires. And a few wires does make a big deal. But when if you're an Apple or somebody and you're going to implement 10,000 of these sensors, this is a huge savings in wiring. So similarly along that line, this is a safety application where instead of a sensor, we're using a light curtain or a door interlock safety switch. And within safety, first of all, everything's yellow because it's be redundant. It's much faster reacting, and it's just really dedicated to basically stop the machine in the event that one of these things becomes interrupted. Traditionally, and you look at a company like Applied Materials, they would have a big giant machine with 50 different door interlock sensors. Every one of those door interlock sensors is home run back to a relay, like an ice cube relay from 1950, basically. And if you've got all those sensors, you need a relay for every single one of them. What we invented 2 years ago is called FlexiLoop. So this is a way to use the same kind of loop architecture that you have in an Ethernet system and use it to connect safety devices. And the great benefit of that is I have one safety I/O here that I can monitor up to 32 devices. So right off the bat, I'm eliminating most of the relays and basically most of the logic, because we want all of this stuff to basically do the same thing. If I break the light curtain, I need the robot to shut off so it doesn't, chop my hand off. And it's basically reduces, this is the node, like you could imagine an Ethernet node that's monitoring the sensor and providing power to it, and then each of my nodes is then addressed. So not only do I reduce all my I/O, I can actually know exactly which of the devices has been tripped because I can monitor the individual node. In a typical, circuit that was just connected in series, you wouldn't really know which one was broken. You would just have to assume one of them's broken. I better go check all these doors and get that fixed. So, huge benefit in, of course, wiring, uptime, and the amount of relays. Big cost savings there for big companies. But this is difficult, again, to implement. If the customer isn't using 6 safety, this is a problem because this has to be our safety control interfacing with it. If they're using an industrial PC, we'll have some communication issues. But this one in particular has so much upside that, makes huge sense to implement it. And some new technologies too. So if you guys remember this movie, the cute little robot. So when I saw this sensor a year ago in Germany, this is exactly what I thought about. It is really a set of eyeballs for a robot. And then this is the kind of thing it could do. And this is the imagery you end up with. You get some funny occlusion here, but the huge benefit of this technology, which is basically the video game, the Sony Kinect, we waited till Sony's patent ran out of that, and we just basically industrialized this technology. So it is a structured light. You're emitting, a point cloud from this little lens, looking at it with 2 different cameras, giving you a triangulation position. The huge benefit is really here when we're doing dimensioning. In the past, I would have to move something past my laser and my camera to get 3D data from it. Now I can just do that with a snapshot. And this helps for collision avoidance. This helps for, pattern recognition, a million different things that really brings the cost down of technologies. And this is another example of, the camera on your cell phone is probably better than the camera that I'm going to sell to, my customers, which is kind of insane, but that's kind of how it ends up working. And I'll show you kind of an example of that. Let's get back to... Well, let's show the movie, and I'll show you that. So, and then this is a movie. Let me make sure my volume's up, or I'll have to... see if it actually plays.
Over the course of thousands of years, evolution changed nature. Over the course of thousands of years, evolution changed nature, adapted conditions to its environment, and changed animals and humans into what they are today. Now, another evolution is to be expected, an industrial evolution. Because the much talked about and predicted upcoming industrial revolution will be an evolution of goods and services. It will make the impossible possible. It will change products, locations, and materials into independently operating objects by implanting a DNA chip. Get ready for it. The network will be the indication of the production of the future. All elements will be connected and able to communicate with each other. The network as an example of perfect organization. Every move and commotion will be immediately transferred as information. In terms of production, this means, in the future, once an order is placed, all locations of production will be automatically informed. The various machines and production phases will communicate with each other and coordinate who will do what at what point of time. Future products will carry all information with them and independently tell machines which individual operation is necessary. This means that we're dealing with intelligent resources and products. Production will not only benefit from internal communication, but also, as it is called in nature, from swarm intelligence. Connected people operate together and are therefore more productive, stronger, and faster than people acting alone. To adapt, to react to changing situations. Not only in nature is it necessary to be flexible to survive, the market is also subject to constant change. But how to respond to this change with the help of new production methods in the future? Through originality? Through following the trend of individualization or meeting customer demand for custom-made products? Through the integration of clients in the development process? Through flexible design? Through product development that can quickly adapt to the current market situations? This poses high challenges to industrial production, especially to product development. One solution is direct production. The design is delivered and then quickly translated by a 3D printer, which is connected to the development and production location. The individualized product seamlessly enters the industrial development process of the end product. Hereby, customer requests can be met, market changes can be responded to, and a wide supply spectrum can be generated for the same product. There are no further costs for extra storage room or workforce, and of course, there is the joy of the product's variety. In the future, logistics will be facing major challenges. In order to get future production working, it will be even more important for deliveries to work on short notice, since market changes and unexpected complications always need to be taken into account. The future calls for an even faster response, but in order to reach that, we need a new way of thinking in transportation. Besides the prevention of transportation through local production, there will also be new forms of logistics. Interconnected drones will guide themselves. They will be guided and programmed by the intelligent product, which stores information and therefore knows where it needs to go. The future information network between customer, supplier, and intelligent product will ensure flexible logistics that can quickly cater to any demand. In the future, machines will coordinate themselves and will therefore process orders in a more focused and collective way. That means logistics will only be needed when there is a demand, communicated and planned within the network. In the future, one of the main tasks for companies and employees will be continuous training. New technological possibilities require a different awareness and new flexibility from all employees. This includes work times, the tasks of respective colleagues, and variable organization of working time enabled by the companies. Long-term, the working environment will change. This means that physically hard work, as well as tasks that are dangerous to health or technically simple, will diminish. This can be a challenge and also an opportunity. People will then have the tasks of creativity and design, the guidance and control of entire processes, as well as the control of quality and responsibility for correct actions in exceptional situations. Employees are the interface between constantly flowing information. They are the controlling authority. The relationship between humans and machines will be raised to a new, more natural development level. Employees will be deployed in a more focused and therefore efficient way. In this case, we can only learn from the best in the field. Every employee will therefore have particular, customized tasks. Get ready for the Revolution 4.0. Because the future is closer than you think.
So, pretty cool stuff. I think it's ambitious, right? I mean, I think I look at this stuff, and Charlie, you brought up the fact of the human factor of all this, right? I think there's a big opportunity for creativity there, but you know, when we put 1 million robots in place of 1 million people in China, it'll be interesting to see what those 1 million people will end up doing. Hopefully it's better than what they were doing before. So, and I don't know why there's so many animals in that video, but whoever made the connection. So I'll finish up with this last product. We're a few minutes over, but not so bad. So this one we use all the time. This is a very common product now in automotive. And what it basically does is it's the eyes of the collaborative robot. So we're scanning a big bin of, these are piston rods in this case. And why this has been so popular is that, and let's take Tesla as an example, they can order, or rather manufacture parts and have them shipped in unsorted boxes. If you had a person picking from this bin, you'd probably have to put them in cradles or nest them in some way where a person could more easily pick them out. The robot doesn't really care. As long as we can basically produce a good image of the part with our laser there, and assign and basically coordinate that with a CAD drawing of the part, we can tell the robot exactly where to pick it up with the properly designed gripper. And of course, this is where the whole gripper thing comes in. The gripper has to be basically purpose-built for whatever part it's going to handle. So we get much more usability as gripper technology increases, obviously. But these sort of operations are great because it's really, bits like this where a person couldn't pick it up, a big V8 engine block like that, or just tasks where you're going to injure yourself if you keep doing this stuff over and over and over again. So we're trying to bring this in, and the tricky part is essentially, A, can I image the part? I've got sensor challenges there, and then B, can I design a robot that can pick it up? We're working with Dole right now down here in Salinas to pick and sort strawberries. So obviously they're squishy, it's very cosmetic how they need to look, and it's a menial task. So this is something we're really looking forward to solving. So that's PLB, and we obviously do the same thing for racks. It's just the same system looking sideways. So lots of fun stuff in the future. It's just a matter of getting customers willing or having the need to implement something like this. And the cost of a system like that, the sensor is maybe $50,000, and the robot's going to probably run you, what, another 80, would you think?
Far too much.
Yeah, well, lots.
They're coming down rapidly.
Yeah.
Automotive would be 15.
15 for the robot, yeah.
Yeah, and the small one is 30 kg.
Yeah.
It's even less.
So you're going to make me have to bring the price down on my sensor, damn it.
You can't make a robot.
I know. And it's funny too. The technology changes so fast. Universal Robots has been. I know. I work with their salespeople here in the Bay Area. They can do no wrong right now. They're selling so many robots, so it drives vision system pricing down. Just like there'll be a 3D camera on an iPhone on the 7 coming next year or so. I'm sure that'll drive our cost down further. So it's cool to see that the sort of synthesis of the technology is out there. It's going to grow faster in certain areas, and then we just need to adapt to it. So that's all I got. Does anybody have any questions, Charlie?
Yeah, quickly, Cameron.
Yep.
Your Tesla application.
Yep.
You're looking for something. You know what you're looking for because you have a CAD database.
Exactly.
Your case with Dole with strawberries, you kind of know what you're looking for, but you don't have a CAD database for the
Yep.
strawberry.
Yeah.
Then the ultimate application is, can you look for a broad range of parts with no CAD database?
Yeah.
I was mentioning earlier that Amazon has an example in there. If you go out here in Tracy to the Order Fulfillment Center,
Of course.
8 million SKUs. And so Amazon can't work from a product database for bin picking or
Yeah.
anything else. They're going to need technology. I'm just curious, is that in the SICK product roadmap with?
It is. So we have a funny marriage with the algorithms that do that picking. So I typically sell the sensor, and I have to partner up with an integrator like a Concept Systems or Scythe, or even like a Halcon or a LabVIEW that writes the algorithms to do that detection. So in a good example, it's not really depicted here, but with 3D camera, we're doing stuff at Amazon where there's just a bin, nobody knows what's in it, we need to look at it and determine how to pick it. We call it neural networking, but we just basically show the camera so many different situations that it knows, well, there's a square box, I know I can grip it, and man, some of the scenarios took 30,000 different views to show the system to have it create these algorithms. So yeah, that's a big deal. Or just to track something where you don't know necessarily where it's going to go. So when we do a lot of sorting and dimensioning with big logistical companies. So we throw a box on a conveyor belt. We don't know how big it is. We don't know where the barcode readers is. And just by getting an initial dimension set that tells us kind of the rough dimensions, and then instantly, and this is in the case with Amazon, we can image a product, give it some dimensions, and then they can make a box that suits it right away. So yeah, that's a big part of our business, but it's often a challenge because the customer goes, oh, give me a 3D camera. I want to do a bunch of sorting. It's like, okay, well, here's the camera. And he goes, well, do I just point it at the object and it just works? No. So I mean, I would say getting the optical view of the camera is 10%, and then the other 90% is writing these algorithms. It's a huge expense. So that's really, the more we get in software development to utilize 3D, the quicker that will get. But it's a total pain. I mean, with Dole, for instance, we just create parameters. We basically say the strawberry is going to be of some certain size. You can probably pick it up at this angle, but they want them orientated perfectly so the stem is in one direction. Same thing with romaine lettuce. So, and when you start picking food products, we do this with grapes, they're always going to be different. So you have to have loose and kind of mendable algorithms to know where to pick and then how to derive data from that. But yeah, software is the biggest part. I mean, in this camera we talked about data. This thing will stream at full tilt a gigabyte every 3 seconds, and we have to sort through all that data to determine what are the gems in that data set. So that's the biggest challenge. People look at it and go, well, I can see it with my eyes. Can't the camera just see that and make the same decision? And it's no, your camera doesn't have your brain. So.
Are structured light applications a bit slower in real time?
Not really, because if you think about the scan time to actually scan an object, paralleled with actually just looking at one, the processing is kind of similar, but I have to move the object with my 3D camera to get that data. So there's lag there. Even though it can acquire that much quicker, it's just acquiring 100 micron 2D profile of it. So 3D structured cameras, it looks a lot more like live video, much more so than a line laser would ever do. But of course, it doesn't react that fast. Time of flight is the speed of light, but of course, processing that and getting data out of it is usually the trickiest part. The image will react very quickly, but I would say it's still in the milliseconds to process something. We can do, we're with this camera at Southwest Research Institute, we're looking at boxes sliding down a chute at some unknown speed, and we're able to kind of determine how big they are and how to grab them.
How good is the point cloud you have?
Yeah. These are just infrared, and I think, I don't really know what the point cloud looks like. You can see it's relatively high density because every little spot you see in this purple guy there is one light. And then the other version of this camera is it's just stereo vision, which has other benefits. It's probably faster. So.
Oh, right. Okay, I'd just like to know what about the reliability of the sensors when it comes to outdoor usage, especially with the extreme weather conditions and
of course.
thunderstorms. No.
In the case of, when we're with 3D outdoor, typically what we're using outdoor is the LMS products. So an LMS from SICK is like a laser on a siren. It's going to scan 85 meters in one sweep. We have all sorts of technologies to deal with fog and rain, and we usually just use different sampling. So we make one scan at a certain speed, and we know I'm probably going to hit a bunch of raindrops. And then I make, it's called multi-echo, more than one scan to determine, am I seeing a raindrop or am I seeing some structure? So, and you're constantly filtering those signals coming back to determine, is it a solid object am I detecting, or is it rain or fog or dust, or so in those situations it's pretty reliable, especially in weather, unless it's like a complete whiteout snowstorm or something like this with LMS. But and those are the few ones. So if you drive down the freeway here, you see this kind of thing. It looks like a little horn or something suspended over. This is our sensor that's basically looking at a truck going by, making sure it's not too big to go under an underpass. And it works all the time.
Those are done basically in the software? Or,
Yes.
Well,
Yeah. Well, the sensor's always working at the same rate. We just determine what bits of data we want to grab from it or what we want to filter out. Because obviously you're going to get a whole bunch of noise, especially in the fog. So, but in like your type of applications with the smaller ones, hopefully, well, maybe it could be dusty or something like that. But scanners, all of this stuff is very susceptible to dust. I get calls from customers all the time. Your sensor sucks. It doesn't work. I go over there and I wipe it off and it works fine. And you're just like, oh my God. And there's even, the sensor will tell you this, but the maintenance people typically maintaining them don't know that. So it's kind of funny, the little things that the best technology in the world, if they don't maintain it, it isn't going to work for very long. So, all right, we're running a little short on time, so let's hand it over to Utku. And are you going to plug in your?
Yes.
Cool. Thank you.